Welcome to video 12.4 day 1. I know this is a little odd because we finished 12.2 and now I'm jumping to 12.4. We are going to go back and pick up 12.3, and I just want to kind of point out a few things that 12.3 is going to do. 12.3 is going to work with the difference quotient here and take the limit as h approaches 0. And we will learn that that will give us the slope equation for any tangent point on that graph. And we've done this a little bit when we did some conics, but you will really like how easy this is. Then we will also discover that this same equation gives us the velocity at a specific point in time. The instantaneous velocity, actually. Okay? Those are the big things that we're going to do in 12.3. This lesson focuses on this being something called a derivative of a function. And we are going to learn a couple different ways to do this in this lesson, and then I will teach you 2 more in day 2. But I just want to let you know that in 12.3 we are going to touch on those things right there. But there's a shortcut to doing this, and it's with the derivative that they teach you in 12.4, and that's why we're going to show you this first. So I'd like you to pause the video for a minute and copy that down, and then we will talk about it. So when you have the notation for a derivative, there are many different ways you can do it, and it will depend upon the author of the book or your professor, your teacher, how they want you to write it, to denote it. But a lot of times you will see this is what you will see in our book usually, and you would read that as f prime, or the derivative of f. All right, this would be y prime. Sometimes you'll see the differential of the function in respect to x, or the change in y with respect to x, dy over dx. You'll see this notation as well. We usually use f prime of x. Okay? So the first major way to calculate the derivative is using what's called the power rule. And the power rule states that if you have a function that is a power function, x to the power of any real number, okay, any real number can be in that exponent, then the derivative of that function is taking that exponent and bringing it down in the front, multiplying it by that coefficient. Right? There's just a 1 there, so you would have become n times x, and then you lower the exponent by 1. And that's really the only process. It's not a hard process. I want you to pause it right now and write down those 4 examples, and then we will do those together. Alright, so if I have the function j is x to the 4th, then j prime would be, bring the 4 down in front times that 1, so I have 4 times x, and then you lower the exponent by 1 to the 3rd. You're done. The derivative is 4x cubed. Let's do function h is 3x to the 5th. So that would mean that the derivative would be 5 times 3, or 15, times x to the 1 less to the 4th. You're done. Okay? Let's look at example 3. G of x is 6. Y is equal to 6. That's a horizontal line. Okay? But I want you to imagine that, because there's no x, there's an x to the 0. Anything to the 0 power is 1. So if I put that 0 there, then you can think of that as just 1. I haven't really changed the value at all, but now you can bring that exponent down. 0 times 6 is obviously 0. So the derivative of this would be 0. But think about it. This is a horizontal line. All horizontal lines have a slope of 0. So that makes perfect sense. All right, come over here. Function k is equal to the square root of x cubed. Now I know that can be simplified, but I'm going to encourage you to write it as an power function. So you have x to the 3/2. All right, bring the square root can be written as the exponent of 1/2, and it's cubed. Now when you take the derivative, again, bring the exponent times the coefficient, so 3/2 times 1 is 3/2, times x, lower that by 1, 3/2 minus 1 would just leave you with 1/2. Now, this function was written in radicals, so let's write it again. Let's write our answer that way. Okay, and you are done. Now let's put some of these properties in technical mind here. All right, so if I look at these examples, I'm going to give you 2 right now that I want you to pause and write down, and then we'll talk about them. So this property talks about if you have a constant, and this is referring back to this example here. You have the function of an integer. Then the derivative of that is always, always, always 0. Okay? If you have a constant multiplier or coefficient here in front, and it can be positive or negative, any integer right there, right? Then the derivative is going to be that n times the c and then times the x with the reduced exponent. We did that right here in example 2, where we brought the 5 down times the 3. All right, that's an example of this property right here. Let's look at another property that I have. The next one is a sum and a difference property, meaning if you have a function that has many different parts, functions, inside, or different pieces of a sum or a difference, then to take the derivative of the main function, you just take the derivative of each of the parts. Okay? Let's look at example 5. Example 5 has a function of 2x to the 5th minus x cubed minus 102. If I want that derivative, that's simply 5 times 2, 10, times x, and then I reduce the exponent by 1, minus 3 times, there's like a negative 1 right there, so I would have a negative 3x, lower that by 1 squared, and then the 102 is an integer, it's a constant, so that, thank you, the bells are ringing because I'm doing this during lunch. When I take the derivative of the negative 102, it's 0, so I don't even need to write that down. All right, let's look at example 6. Function is 3x to the 4th times the sum of x plus 2. Now, this really is a product of 2 functions. And you're going to learn in day 2 that there is something called a product rule. And we could do that on this problem. But for today's lesson, I'm just going to distribute that 3x to the 4th. And I'm going to get 3x to the 5th plus 6x to the 4th. And then I can take the derivative of each one, right? So then I would take the derivative for g would be 5 times 3, which is 15x, and I would reduce the 5 by 1. I would have 4 times 6, which is 24, times x to the third. Alright, I'm going to let you copy example 7, and we'll talk about that. Example 7 is a huge division problem. Well, again, in day 2 of 12.4, there's something called the quotient rule, and we will talk about that as well. But for today's purposes, I would like you just to split this up into 3 fractions. So let's just make 4x to the 4th over x minus 3x squared over x plus 5x over x. And then let's clean that up a little bit so that the function of h is 4x cubed. This would be minus 3x plus 5. Now I can take the derivative of each term because of the sum and difference property that we had. Right? So the derivative of function h would then be 3 times 4, which is 12, x, reduce the 3 to 2, minus, there is a 1 right there, it's understood. So I have 1 times negative 3, which would be negative 3. I reduce that by 1, so it's gone. And the derivative of an integer is 0. Now, the second type of derivatives that we're going to do today are the chain rule. And that's because you're going to link them together. So you pause it for a minute, copy that down. If you have a function f and you have inside you have another function, so you have a composite basically, you have a composite function, then the derivative is taking the derivative of the larger function, the f, times the derivative of the inner function. So it's called a chain rule because you're linking these together. You're linking the derivatives together. You're unfolding the composite, basically. Let me show you here with example 8. Example 8 says that function f is x squared minus 6 squared. So what we're going to do is we're going to take the derivative of the larger function, which really would just be x squared, would be the f function, so to speak. And then the g function would be this x squared minus 6. Okay? So if I take the derivative of the larger function, I would bring that 2 out in front and I would reduce it by 1. So I'm going to have 2 times x squared minus 6 to the first power. Now the g, the derivative of the inner function, would then be the derivative of x squared is 2x. The derivative of negative 6 is nothing. Now I need to clean that up. I've got 2 times 2x. I've got 4x times x squared minus 6, or 4x cubed minus 24x. And that is my derivative. Now, I want to show you that some of you, and you can also do this on Friday, but it will be a little more confusing. It'll be a little harder to do this on Friday, on the next lesson on day 2. So I want you to think about this for a minute. If you have this function of x squared minus 6 quantity squared, you can write it like this. And you can actually FOIL that out. X to the 4th. My middle term would be a negative 12x squared. My last term would be a positive 36. And then, applying your property of sum and differences, you would just take the derivative of each term. So the derivative then would be, bring the 4 down times the 1, so I have 4x, reduce that to the third minus 2 times negative 12 is negative 24. X, reduce that by 1, so it'd be 1. And the derivative of the 36 is 0. Well, look at here. That's the exact same derivative. So in some instances, the chain rule is, you may prefer to just multiply it out and then take the derivative of each term. Now sometimes you are going to have a function like this, and we will start here when we come back in the second video to take the derivative of this function.